everyone. I hope you enjoyed the first part of this event and also the food. Now we are ready to start the second section of the program, where we will have 3 speakers who will take us into their work and the impact they are making. Our first speaker is a professor from the University of Agder at the Department of Engineering and Science. His research interests involve computer engineering, robotics, and also the interaction between humans and robots. So it's a great pleasure that I invite on this stage Sanfilippo, Professor Filippo, who is gonna talk about the complex relation between AI, robotics, and security.
Thank you very much for the nice introduction and for having me here. And the theme of this event is safety, and in particular I will take you into a journey which is about humans and machines collaborating together. So in that kind of collaboration, safety is a priority. The title of my talk is Human-Robot Teaming, a forward leap into real-life applications. So the work that I'm going to present and the research that we have done, it's a work of several people, and without them, this presentation, this work will not be possible. So that's why I am always very proud of our team. In this figure, I've also summarized not only the people doing the research, but the research itself, and it's organized into 3 main layers. We have the core layer that is represented by robots operating in different environments, from aquatic environments to land to aerial robots. These for us are carriers. They can be used to carry sensors or equipment around for different applications. On top we have add-ons that we can add on top of the robots, like manipulators, grippers, and so on. But the core layer that we really focus on is this layer here, is the human-machine interaction layer. This is the layer that connects machines to humans. So let's dig into the core of my presentation today. I will first pay attention to this figure here, which represents a revolution. In the last 20 or 30 years, we have gone from caged robots, so robots in a cage, like you are in a zoo and you have, wild beasts caged there because they are dangerous for humans. Safety is a priority, right? So 20, 30 years ago, we had robots living isolated in a cage, and humans were not allowed to enter the cage because these beasts have very high torque, very high velocity. It's very dangerous. A potential impact with humans will harm people. So this kind of paradigm was still a big step forward compared to manual work. We can automate the process of production, especially for tasks that actually do not require humans. So for example, a production line, manufacturing cars or for the automotive industry. But later on, moving into human-robot interaction, we realized that there are tasks that actually require the involvement of humans. And finally, we started liberating our lions, our beasts, from the cage. We removed the cage, and finally, we start seeing humans getting closer to the machines. But at that point, there is still a virtual separation between the human and the robot. So basically there are no contacts here. Moving on, we started looking at collaboration. So here with human-robot collaboration, we have tasks that are finally done collaborating. So in a sequential way most of the time. There is no cage, the space, the gap between machines and humans becomes smaller. And moving on, we literally see humans finally touching machines with physical human-robot collaboration. So for the first time, you see this progress from a robot in a cage finally touching humans. So of course, when we see this progress, the importance of safety will increase, because now we have humans and robots really close collaborating with each other. But as you can see at this stage, the human is still in charge. You see this light bulb here in this figure? He's the one taking the decision, telling the robot what to do, maybe grabbing the end effector of the manipulator, moving it into a certain point, and continuously collaborate with the machine. But what we are working today, what we envision, is this new concept of human-robot teaming. So at this point, humans and machines are sharing space, they work in the same space, they share forces. For example, one task could be to lift this table. Maybe this table is heavy, I need someone to help me, maybe the robot on the other side. So we will lift this object together. So we will share forces. And also we will share decisions. So who is in charge at this point? Is the human or the machine? It could be a shared decision process. For example, where do I want to take this table to? Maybe to the other room. So the robots need to understand my intention. So at this stage, it's not enough to understand what is happening right now through the use of sensors, like we used to do with mechatronics, but we need to anticipate the intention of humans. We need to predict future. So to achieve this, we need three essential elements. We need better sensors not only on the robot itself, but also sensors on the human, so wearable sensors. We sensorize the human. We also need sensors in the environment, so in the room where this kind of collaboration or teaming is happening. And we also, the second point, we need better actuators, so motors that are designed for a very close collaboration where we share forces. That's why we are designing new actuators that are elastic, similar to human actuators. So if there is a collision, even passively, some part of the energy will be absorbed. And the last point to achieve HRT is better software, better algorithms. And today, finally, we are seeing this trend with the advent of machine learning algorithms and artificial intelligence. We finally have the tools to achieve better algorithms. So within this perspective, we are going to see applications into different domains. So for example, smart healthcare, cloud manufacturing, sustainable manufacturing, smart education, supply chain management, and disaster management. In all these applications, safety is a priority, since we have this close interaction and collaboration, teaming between humans and machines. The first example is within assistive health. So prosthetics and orthotics are one of the best examples where this symbiosis between humans and machines is realized. Actually here we have a cyborg, right? Partially human, partially machine. So within this kind of application, we have designed our own actuator. It's a new actuator that we call it hybrid, because it's partially rigid, partially soft. It means that it's mimicking the knee or the articulation of the upper limbs like humans. So the motor shaft, we still use a rigid motor, but the shaft of the motor is connected to a torsional spring, which is engaged when we have a collision. So safety is achieved even when power is completely cut. If you remove the power supply, this actuator is still intrinsically safe. So, by the way, we care about releasing our research openly. You can download all the design and the software on that repository on GitHub. This is the exploded view of the actuator. So as you can see, it's all 3D printed. We use a traditional motor, and this is a simple elastic mechanism to make this joint partially soft. So of course it's a compromise between torque and safety. And here we have a demo I would like to show you. where we simulate admittance and impedance control, which basically gives us an idea of how humans can interact with this prototype. So now we will see a collision with the human. And as you can see, this collision is safe. The robot will detect that collision and adapt to this situation. So moving on, at this point we have learned about the foundation of how we can build a manipulator. If we look a little bit at the industrial situation today, we have several vendors producing industrial manipulators, like the one from KUKA, these orange robots. And one of the main barriers that we see to achieve human-robot teaming and to open the software architecture for this kind of robots is the fact that vendors have this aggressive selling policy to sell hardware at a very competitive price, but then if you're a company and you want to connect different robots and add sensors, you need to buy software because they developed a proprietary software architecture. So that's why there is a chain here. There is a closed software. So to break this chain, we developed the first open source library for industrial manipulators. It is currently the only one available for KUKA robots in the world. And it works as a bridge between the manipulator itself and a computer program that you can develop on with an external software. So just to jump into applications, I would like to show you two demos that use this library here. Again, interaction with humans. The first one is a simple interaction through a mobile device. This is done wirelessly, and you can control the manipulator axis by axis, or one of the main advantages to use our library is that you can develop your own control algorithm, your own kinematics and dynamics model. And then you can do a little bit more complicated things like use gestures to control the robot. And you can see in real time we can publish the sensor values and comparing the actual position and the desired position in Cartesian space and into joint space. So we are talking more and more, we are seeing more and more this close interaction between humans and robots. Here we can imagine an industrial plant where we have different workstations, right? So imagine like a plant where we are producing, I don't know, packaging milk. The operator could grab the package from one workstation, bring it to the next workstation, maybe for labeling or painting or doing another operation. So we have used a LiDAR sensor to monitor the position of the operators working in this plant. So the blue trajectories or paths are operators moving around. And based on this data, we realized that we can actually predict where the operator is going ahead of time, and then we can adapt the production to that situation. So for example, we can slow down one robot and avoid the potential collision. But with the same data, actually, today data is gold, is the new gold. We realized that with the same data we can also do anomaly detection. So imagine a person that is not feeling well or simply feeling tired or needing going to the restroom. We can detect that anomaly and we can then adapt to that situation. And one more thing is, people work with different locomotion gates. Each of us has a signature locomotion. So we realized that with the same data we can also do identification. We can identify the operator working in the plant. Of course, some of these things have very challenging ethical issues, but of course not all this is needed for all applications. So there are cases where detecting anomalies or identify the operator is required. So at this point, we had an overview of how we can build actuators, how we can control manipulators, how we can adapt to different dynamic environments. So one of the main challenge to achieve human-robot teaming is the complexity of this problem, right? You have seen that it's not enough to know what is happening right now, but you need to predict the future. This is very complex, and especially humans are very unpredictable. So one way to achieve this, or to kind of cope with the complexity of the problem, is to move some of the complexity from the software or the algorithm to the mechanical design. So we can try to find a trade-off. So, and we can see this with an example. I would like to show you how we can build a manipulator. So if we look at the human end is a very complex system with more than 20 actuated joints. So it's very difficult to replicate. One possibility could be to find a way to scale the complexity up and down. So for example, if I am a company and I come to you, I tell you, I want to package milk. Can you build a manipulator that is enough for me to grasp this package of milk? Maybe, we don't need 5 fingers to grasp that package. Maybe 2 fingers is enough. In this way, I can design for you a manipulator that is low cost and it is also scalable. If tomorrow you come with another product to commercialize, we can add another finger if it is a bigger shape. So we can reuse the design. So basically, we have not invented anything. Lego bricks, right? Each of us know Legos. It's the same idea applied to robotics. Modular design, we have a modular palm that you can build by connecting together these bricks, and then you can attach your fingers on top and you can configure them in different shapes. And obviously the most interesting configuration is the one with an opposable finger, because this is how humans grasp objects, right? This is what differentiates us from chimpanzees, right? So by using this approach, we can build a manipulator that is a compromise between a simple gripper like the Festo kind of gripper and a more complex human-like manipulator like the shadow hand on the right side, which is very expensive, right? We are in between. Of course, our manipulators are not really human-like in the shape and design, but they are functional. So at this point, we know that by using the Lego idea, we can build a gripper. So how can we then use it with humans around? So we need a way to detect collisions. So here we have used a low-cost approach. We have hacked the standard servo motors by removing the case. Engineers like to take things apart. We have soldered an additional cable inside the internal potentiometer. Then we can read the change in current and estimate the torque, and therefore detect a collision. So at this point, we know how to design a manipulator in a modular way. We know how to detect the collisions. How can we then control it? And to do this, I wanted to show you this idea. You know this doll, right? In French, it's called marionette. This is a very nice example that shows you that you have just a limited number of threads here, and through this you can control the movements of this doll, right? Multiple joints, just a few number of inputs. It turns out that this is exactly the way how humans operate fingers. So for example, if you try to take your index, please. Try to move only the last phalanx, only the last link. Can you do it? Maybe some of you are piano players. In general, we cannot do it, but if we repeat the same experiment by locking the first 2 links, just use the other end, lock the first 2 phalanx. lock them, then you can actually do it. So it means that mechanically our fingers are able to operate, to move the last phalanx. But it's our software, actually our firmware, I would say, that operates in this way, as in the marionette. If it is as if there was a thread, an invisible thread, that our brain is pulling and releasing, right? So that these three joints move together in a synergistic way, right? It has been proven by psychologists and biologists that actually this is the way how humans work. We have two sets of invisible threads. One is this, open and close, and the other one is orthogonal to the first set of threads and does this movement. By combining these two, we can approximate more than 90% of grasping operations or movements. So this is very powerful. And by the way, why did I say that this is our firmware? If you have seen newborn babies, right? If you give them a finger, what do? They grasp it, right? So this is already there. They don't need to learn that. It's transferred through generations. That's why it's our firmware. And also it has been proven that this is not only the way we operate, but it's the most efficient from an energy perspective. It means that because of our evolution, we needed to survive with very little food. Norway cold winters, right? We need a way to grasp objects that is efficient. And this is the way we have learned during our evolution. So by using this idea, of course, we can write, engineers like very elegant mathematical equations. I will spare these equations for this evening. I will just jump into the demo. So by using this idea, now we have a digital twin. So you see the visual gripper and the actual manipulator connected, and she is wearing a mind wave headset to read brain waves and control the gripper and grasp a balloon, which is a complex task because we don't want to squeeze the balloon. It's like grasping an egg. So in the next plot, you will actually see how it works. So on the top of this plot, you have the inputs coming from the headset. So it's alpha and beta waves. And down we have the torques of the motors going up when we have the balloon in between the fingers. So at this point, I know that the presentation is very packed, but I still wanted to give you a full overview of the research we are doing. So at this point, we know how to build the manipulator, how to control it from the human perspective to the machine, right? What if we can close this loop? What if we can give a feedback signal from the machine back to the human? This is what we will see in this demo with wearable devices, like this set of gloves that we have designed. These are Biltema gloves, but they are equipped with motors at the fingertips, and we are actuating the motors, making them vibrate when there is a collision, a visual collision in this case with the piano. So he's playing in VR visual piano and receiving the touch and the force feedback from pressing the keys. So imagine that you can use these kind of wearables to control the manipulator and receive a feedback of what you are touching. So touch becomes a very essential, important way of interacting with humans in this concept of human-robot teaming. And touch is also is one of the strongest sense we have in terms of safety. For example, when you drive in the highway, in the motorway, and you touch the edge, you have this vibration bumps. There is a reason, because you immediately react to that. You don't need to see, you don't need to process, right? So touch is very strong in terms of safety, and here we are using touch to train surgical doctors. So on the left side, we have our colleague Teria, who is wearing the device we have designed. We are recording touch. In the 80s, you probably are a new generation, but Sony released the Walkman. It was the first time humans could record music and play music in their pocket, right? We are doing this for touch. We can record the sense of touch, so what the doctor is doing and touching the human body, and the student here we will play the touch sensation, and she can learn to operate the same way the doctor is doing. So I'll show you this video. So there is no audio because I would like to explain what is happening. So this video has been recorded at the hospital simulator at UEA in Grimstad. And here we can simulate different vitals for the patient. And the doctor here is going to perform what is called palpation and percussion on the abdominals. So she can then, all the forces are then recorded and transferred in real time to this other device that the student is wearing. This device is already a commercial product that a startup from Italy has developed, while the recording device we have designed. The resolution is quite good already. We can even sense the palpation. We can sense the pulses of the heart, the heartbeat. So, and this is part of a European project that we have with the University of Siena in Italy and Kaunas University of Technology in Lithuania and the hospital in Lithuania. So moving on to the last topic of my presentation today, again, safety, this conducting thread across all the applications that you have seen today. We are working with the Center of Emergency Management, CM, which is another research center at UEA, to develop a robot that is inspired by nature and looks like a snake. Why do we want to do this? We want to use the same capability of a biological snake, operating across different domains, navigating through sand, climbing trees, flying, even gliding, swimming. If we could mimic this with a robot and give this robot to our first responders, we would have a very strong tool to save life and to increase safety of people. So to do this, we have provided our own definition of perception-driven obstacle-aided locomotion, because this is a very special robot. With a normal mobile robot, like a robot with wheels or tracks, you normally want to avoid obstacles, right? You don't want to kill people, you don't want to collide with obstacles. But with this, you actually want to have collisions. It's the only way for the snake to move forward. We can use our own body to push against obstacles and propel efficiently. So this is the robot that we have designed. It has a modular design again. It has the same actuators that are soft and can be 3D printed. You can download the design and you can assemble it at home. So this is the last video. At this point, again, within the concept of emergency management and safety in emergency management, we are also using robots that are quadruped robots, so robots with 4 legs, like the dog, and we are training them to use their senses as, a rescue dog. A rescue dog has a very developed sense of smell. Here we are simulating the same with lights. So the robot is able to detect a light source, find the direction and converge towards the light, as if there was, a rescue dog using its nose to find a survivor in a collapsed scenario. So we have tested this in simulation and then with a real robot from Boston Dynamics. So here we are testing actually sound, but sound and smell are very similar or comparable. So we have added 16 microphones array on top of the robot the student is clapping, the dog is detecting the direction of the sound and converging in that direction. In this situation, you can imagine the application. If this building collapses and there are survivors, we can send a robot. If the survivor makes noise, the dog can detect it and converge towards. And of course, we're also integrating other kind of sensors like thermal cameras to detect the emitted heat from the person, combining multiple sensors to increase safety. And this was my last slide. So I'll be happy to take maybe at least 2 or 3 questions. Thanks. Maybe someone? Any questions? Any comments? Any critique? Please.
How long is it currently applicable, the collaboration that you're speaking of?
I cannot hear you well.
Thanks for the nice presentation, Filippo. It was very nice to listen to that. How much do you see it being applicable in the current industries at this moment? Can you see the transition nowadays as well?
Yeah, so it's very hard to answer this question, but I would say that we are definitely transitioning. And again, there are tasks that do not need human-robot teaming. All the tasks that can be fully automated don't need this. But there are tasks, and especially now with the advent of AI, where humans and machines need to collaborate, right? So I'm talking, for example, your field, batteries, right? Disassembling batteries. You have a variety, a plethora of modules. It's not possible to fully automate that process. You need to have a way to transfer knowledge between machines and humans, and vice versa. Maybe at some point, the machine, has seen enough modules that knowledge can be transferred back to the human, right? So there are tasks, and there will be more and more tasks. I'm thinking even about art, right? An artistic process like painting. We have seen robots used for painting, but it's not really painting, it's like a 3D printer, right? You can see the mechanical way of using a brush, but painting with a technique. So for example, oil painting, it's not there. There is no robot yet that can do oil painting, right? That kind of task will require this kind of approach, like transferring knowledge, right? Control the pressure of the brush with the expression, with the emotion, right? That's not there. I think it's gonna be the next frontier, but here we're talking about work for 50, 100 years, yeah? Hopefully, so until I'm retired. Thanks. Maybe someone else? Okay, good.